In this video, we're going to take a look at the hydrolysis of an acid chloride. So hydrolysis always means adding water. So adding water and cleaving a bond, right? So hydrolysis of an acid chloride is we're cleaving the bond between the carbon and the chlorine, and we have added water. So all carboxylic acid derivatives, when they are hydrolyzed, form carboxylic acid. So I do want to make that point before we start. So all carboxylic acid derivatives every single one of them can be hydrolyzed to form the corresponding carboxylic acid. So that's a really key point to keep in mind as we work through the reactions in this chapter. So with a really reactive carboxylic acid derivative like an acid chloride or an anhydride, this hydrolysis would take place with just neutral water. As you move to the less reactive carboxylic acid derivatives, so those would be things like esters, amides, nitriles, you're going to have to use either an acid or a base catalyst. Just water won't be a strong enough nucleophile to do those reactions. But with your highly reactive compounds, such as your acid chlorides, when you add water, what you're going to end up forming is you're going to end up forming the carboxylic acid, and you will also have generated some H3O plus and some Cl minus. So some aqueous hydrochloric acid. And if you wanted to prevent that acid from building up in the solution, you could also add pyridine to absorb the HCl. So pyridine could also be added. So that would react with the HCl. Okay, so pyridine we saw in an earlier video, and that has this general structure. Okay. So let's take a look at the mechanism for going from the acid chloride to the carboxylic acid. It's going to look really, really similar to the mechanism for taking an acid chloride and adding an alcohol to get an ester. In fact, it's exactly the same, except that instead of an R group, you have an extra hydrogen. So let's look at an example where we're not just showing R, let's actually show a structure. So let's look at the same methyl benzoate that we formed in the ester video. So let's say if we had, well, not methyl benzoate, I'm sorry, the same acid chloride we started with to make the methyl benzoate. So let's start with that benzoyl chloride. And if we add water, right, so we can already draw the products. We're going to replace that chlorine with an OH. We're going to get the benzoic acid. And that's the major organic product. We're also going to generate some H3O plus and some Cl minus. We typically don't worry about those. We typically just look at that major organic product. So let's quickly go through the mechanism for this reaction. So I'll redraw that benzoyl chloride. So the carbonyl carbon is your electrophilic carbon, and water is acting as your nucleophile in this reaction. So we're going to have water attack this, and we're going to have electrons swing up onto the oxygen, right? So we break that pi bond and put the electrons onto the oxygen. So what we're going to get here is a carbon atom that is tetrahedral. It started off as trigonal planar, but now it's going to have 4 single bonds, so it will be tetrahedral. And then we have the oxygen with the negative charge, we have the chloride, and then we're going to have the water that we just added. So that water still has 2 hydrogens attached to it because we haven't shown a bond breaking one of those hydrogens. Bonds to hydrogen, so we get this tetrahedral intermediate. So we should label this as our tetrahedral intermediate. Okay, And so what we're going to see here is this is going to collapse and kick off a leaving group. Okay, and we still have this protonated, and so we're going to have another molecule of the water come in and remove that proton so that we generate some H3O+. And we formed the Cl- here. So we see how we're forming this byproduct aqueous acid. All right, so this is the portion that we're really concerned with, is the carboxylic acid, but you'd also be generating these two charged, this salt, basically aqueous hydrochloric acid. But you'd be focused on what's happening to your major organic portion of this molecule. And if you had used the pyridine as well, you would probably have had pyridine come in and take this hydrogen instead of water. So in case you are wondering about the stoichiometry here, why do we just have another water molecule appearing? There is a good chance that water is likely the solvent for the reaction. So what that means, if it's also being used as the solvent, is relative to everything else, you really have an enormous excess of water. So that means it is present in a, we'll just say large excess, even though I don't think large really describes it. It really is an excess relative to everything else. So overall, a reaction is that you can take an acid chloride, and if you see it reacting with water, you're just going to be replacing that chlorine overall with an OH. So this reaction takes place really readily. Acid chlorides are actually very water sensitive, which means if you're working with them in a lab and you don't want it to react with water, you have to take great care to exclude water from your reaction.